can you discuss in further detail what happens to Bmax, Km, irreversible inhibition? So now we are talking about irreversible inhibition. So that's kind of a little bit different because all the consideration that we have for the, or discussion that we have for Bmax and Km is for reversible inhibition, right? It's not for irreversible. So from what context can we look at irreversible inhibition looking at Bmax and Km? Conceptually, mathematically, it's more difficult. Because remember that in order to get all those alpha prime value in the Michaelis-Menten equation, we have to look at the mass balance equation. E total equals to 3 enzyme ES, EI, or ESI. Imagine, like for the irreversible, there are extra terms. So then it's going to be a lot more complicated to change that number, that equation. So, but then conceptually, that might be something that we can address at this point, not mathematically exactly how it's being changed. Conceptually, binding of an irreversible inhibitor to the enzyme active site, if there's any permanent covalent bond formation, enzyme is going to be dead, right? So then, that would mean that in the presence of an irreversible inhibitor, you're always going to have some enzymes not producing product, no matter how much substrate you're going to have. So the Vmax of the irreversible inhibitor, regardless of what mechanism, should be lower, because you're going to kill some enzyme irreversibly. Okay. Km also should be higher in the presence of affinity and the suicide inhibitor. Why? Because in both cases, the affinity and suicide inhibitor, they are competing with the substrate for binding. They are not binding to another site, where different from the substrate binding site. It's the same site that substrate binds to. So it would be quite analogous to competitive inhibition. The Km should be, in theory, be increased. Yes? Yeah.
Next to the base, isn't it actually the substrate? So
Ah.
or like a parent.
Good question. Yes. So in this case, just remember the when we talk about increase or decrease Km, we always compare the Km of the substrate without inhibitor and the Km of the same substrate in the presence of the suicide inhibitor. That's how we compare that. Okay. So then, in the presence of a suicide inhibitor now, with another substrate, since they are competing with the substrate active site binding, right? So then the apparent Km of that substrate can decrease. However, suicide substrate might not bind as well to the enzyme active site as the substrate. So the Km apparent might not even change. Right? If it changed at all, it would be increased. Yes. So in other words, the change of I don't want to get into too much of the Km and Vmax of irreversible inhibitor, simply because this is a very good question to think about during the lab, because that will consolidate how irreversible inhibition works. But then it will not be a fair question to ask in terms of how we think, because we address that to that detail. So let's leave it at this point. Okay. On the exam, you will see all the rate constant using a small case like this, so there's no ambiguity. Okay, so I try to do that for the each interview too. So the rate constant Ki, what's the difference between Ki and K1? So then you have to be really looking at it carefully. This is Ki, this is K1. Yeah. So Ki is the rate constant of permanent covalent bond formation. I would think, try to look carefully on the midterm question. If something like this that you are not sure, you can ask me because I'll be walking around. Yeah, so it shouldn't be like how well focused to discern the eye and one that make a difference, okay? But then it should be straightforward. You really look at that sheet. It should not be too. You should be able to see it. And also, I'm using the same font now as the midterm. It's going to be on this font too, so it's going to look like that. K1 will be the rate constant of ES formation. So by definition, so they are very different. K1 will be how fast S binds to the free enzyme, how fast it binds, basically. The small ki will be how fast, in this case only for irreversible inhibition. Upon binding of irreversible inhibitor, no matter it is affinity or suicide, how fast is that permanent covalent bond formed? That is qualified by or quantified by the small ki value. The bigger is that value, the faster it is to form that permanent covalent bond. This question talks about, I think maybe got lost with the way I talk about HIV protease. This is the part that I talk about the HIV protease inhibitor, the competitive inhibitor, because now we can look at the active site structure of that protease, and then we can find this company can design competitive inhibitor to bind very well in the enzyme active site and inhibit that protease and turn out to be an effective means of treatment of AIDS. So this is referring to the competitive inhibitor discussion. So that is saquinavir and ritonavir. And then the one that has the lower big Ki value, the better it is for binding, the better it is as a competitive inhibitor. Yes? Repeat that, I don't hear.
Do we have to memorize the structure?
Okay, the question is, do you have to memorize the structure of saquinavir and ritonavir? Absolutely not, because I don't think there's any structure that you need to memorize as a whole that I mentioned, even though in the glycolysis or other places you have to recognize what is going on, like you'll be able to discern what's going on from the structure, but not to reproduce the whole structure. Okay, the comment now is going to glycolysis. All those, you need to know the substrate and the product of each of the steps that I talk about, glycolysis, citric acid cycle. Okay. However, you do not need to know to reproduce the exact structure of the substrate and the product. But then you do need to know what is going on in the reaction, right? So for a certain part of the structure, you should be able to follow, or else you cannot address the question. Go over the SketchUp plot, significance of that. SketchUp plot is used for determining the binding affinity of a ligand or an agonist onto a receptor. So always SketchUp plot, we are talking about determining the KD. KD is the tells us how well a ligand binds to a receptor. So we can compare different ligands for the same receptor and see which one actually binds better. If it were a drug, then the one that binds the best probably is a better target to follow up as a drug. So for SketchUp plot, also we simply do the similar thing that we look at the reversible binding of receptor and ligand, K1, K2, that's what I use. And then we have total receptor with the free receptor and ligand bound receptor. Then we do rearrangement of the equation so that we can have a strict line equation. very analogous to the line river plot. Try to get a strict line relationship so that now we can determine the parameter of interest. In the case of line river plot, Km and Dmax are informative. In this case, Kd is informative. So we are simply plotting the R over L. R is the bound receptor over total receptor. So if we plot this way, governed by the straight line equation, the straight line is always going to have go this way, and this is always 1. No magic, just because of the straight line equation that gives you this way. And then right here, the y-intercept is always 1 over kd, and the slope is minus 1 over kd. So by plotting the sketch chart plot, by doing experiment to determine different ligand concentration, and then be able to keep track of the total receptor concentration versus how much of the receptor is bound by the ligand, doing experiment to determine those numbers. Then we can plot the graph. If it is a strict line plot like this, then we can look at the y-intercept, determine the kd. Why is it important? Because it can help us the kd value. And that's all we count. Because we want to find out the kd, then we can compare between different ligands or different agonists. I did mention that the assumption here is that one ligand binds to one receptor, and then we rearrange the term to get a straight line. So sometimes the experimental data will give us some values that are not a straight line. When it is not a straight line, then it means, always means, that there's more than one ligand that is binding on the same receptor molecule. It's not one-to-one binding ratio. Yes, question there.
So the little r being 1, is that because you assume that all of the receptors are bound?
The question is that I said R is 1, do I mean that all the receptor is bound? And in this case, yes, if you want to read off this one, that would be the bound receptor is equal to the total receptor that is always 1. You can conceptualize that one. Yeah.
Is that slope negative 1 divided by kd, or is it just equal to?
The slope is equals to minus 1 over kd, and this is the sample questions. Number of sample questions on the enzyme kinetics. Okay. Let's read this one first. What substrate is the best substrate for the inhibitor? Just look at the substrate as a small Km. The best competitive inhibitor? Yes. The reason is that for the competitive inhibitor, what it is necessary is the binding affinity. The better it is to bind the enzyme active site, the better it is as a competitive inhibitor. So the only parameters we look at for competitive inhibition, which one is better, is the Km value. And then you say, I feel like we should be looking at the Kcat as well, the competitive inhibitor, and so yeah, that's true, that's true. Because the competitive inhibitor will bind well and will not cause catalysis. So small as the Kcat is better it is, that's true. It's true that we have to consider both Km and Kcat, then we should Kcat, right? Both Kcat, look for small number. No, not like this. Because think of what is Km. Km is in the rate constant term. K minus 1 plus Kcat over K1, right? And indeed, if you look at the Km value, you are already looking at the Kcat. Because if you have a huge K-cap, what does that mean? That means once it binds in the enzyme active site, it just turns to the form of product, right? So it appears that it's not binding. So the Km value is high. So just by looking at the Km value, you already take into consideration the K-cap. So whichever one that has the lowest Km, actually already you can look at it as the best competitive inhibitor because the Km value